This demo presents the work carried out by DC1, hosted at the University of Essex for the Xeon project task on the design of semantic encoder and decoder. The work has been conducted at the Essex 60 lab with support from UKRI and the MSCA Doctoral Networks program. Here I will briefly introduce semantic communication, explain how semantic and conventional bit-based communications can be supported together, and finally show how pinching antenna systems can be envisioned for future wireless networks. Let me begin by introducing the key technologies behind our work. First, semantic communication is different from conventional communication. In semantic communication, the goal is to transmit and reconstruct the intended meaning of a message using state of the art neural networks. This allows the system to extract and recover the most relevant information, especially at low transmit power levels. One practical system is known as DPSC, where the transmitter and receiver include semantic encoder and decoder blocks. Semantic communication is particularly useful for intelligent services in next generation wireless networks, where efficient use of wireless resources, also known as spectral efficiency, will become even more important. However, semantic communication will not replace conventional bit-based communication in every scenario. In many applications, exact message recovery is still essential. This means that future networks will need to support both semantic users and conventional bit users together, leading to heterogeneous users communication. Supporting both types of users efficiently requires advanced multiple access techniques. This is especially relevant for 6G, where networks are expected to support massive connectivity, diverse services, and intelligent communication among different types of devices and users. Alongside communication protocols, future 6G systems will also need new physical technologies. One promising example is of pinching antenna systems, where dielectric waveguides and flexible pinching antennas are used to create reconfigurable wireless links. Such systems can effectively bring the access point closer to users and improve reliability and coverage in future wireless environments. Here is a brief summary of our main contributions in the context of future wireless networks. First, we developed a hybrid NOMA framework for heterogeneous users, where semantic users and conventional bit users can be supported within the same communication system. Instead of relying on a fixed access rule, the system dynamically decides how users should share the available resources. We then designed an adaptive user pairing and decoding strategy. In our hybrid NOMA approach, users are dynamically allocated across time slots according to their general conditions. When semantic and bit users coexist, the decoding strategy is adapted to manage interference more effectively. We also extend this research direction towards pinching antenna systems. In particular, we present a promising research avenue by jointly exploiting the flexibility of pinching antenna systems and semantic communication to meet future wireless communication requirements. We now highlight the performance gains achieved by our proposed approaches. On the left, we see that our hybrid NOMA framework for heterogeneous semantic and bit users achieves significantly higher ergodic semantic spectral efficiency than the orthogonal multiple access benchmark. This shows that allowing semantic and bit users to share resources more intelligently can substantially improve system efficiency. On the right, we show results for the pinching antenna system compared with a conventional antenna one. Here, the pinching antenna approach achieves higher average semantic spectral efficiency for different combinations of antenna numbers and coverage areas. The main reason is that pinching antennas offer greater flexibility for wireless access through the waveguide structure. These results show that semantic aware multiple access strategies and flexible antenna technologies can be effectively utilized to support future intelligent wireless services. The main simulation parameters used for these results are summarized in the tables below the figures. Thank you for your attention. For further details, please refer to the papers listed and feel free to get in touch through the email address provided.